So, how to predict molecular geometries. The first step is drawing the Lewis structure. Got to start there. From the Lewis structure, determine the total number of electron groups in the central atom. Then figure out how many bonding groups and how many lone pairs you have. And here's where I differ with the book's instructions. The book's instructions say, refer to table 10.1. Well, that's all nice and everything if you've got table 10.1. Don't do that. Think about balloons and how balloons would arrange themselves, and then imagine that the lone pairs are invisible. And isn't thinking about balloons happier than looking something up on a table? Right? Balloons are happy. Okay, so let's practice. Predict the molecular geometry and bond angle of Cl and O. Now, the way that this formula is written implies the order. So we're going to assume that it's chlorine bonded to nitrogen bonded to oxygen. So we have to start with the Lewis structure. So we'll stick these together. And with this one, even if you put the elements in the wrong order, you'd end up with the same Lewis structure. So, you'd end up with the same geometry. So we've got bonds, and now we need electrons. So we've got 7 from the chlorine, 5 from the nitrogen, and 6 from the oxygen. And that's what, 18? So we got 2, 4, 6, 8, 10, 12, 14, 16, 18. Here's our 18 electrons. Everybody happy? No. Nitrogen is not content with 6. Nitrogen wants an octet. So what do? Double bond. So should I take a lone pair from the oxygen or from the chlorine? From the oxygen. Because when I take and have oxygen share with nitrogen, now I end up with oxygen having 2 bonds, which is what oxygen would really like. Chlorine really likes to have 1 bond. You could do it the other way, but then when you look at formal charges, you're going to have to fix it. So here the oxygen has a 0 formal charge, and the nitrogen and the chlorine. Yeah?
Is that based off the electron affinity?
Formal charges are based off of electronegativity and electron affinities, but we don't have to think about them. Yeah?
I was just saying for deciding which atom creates the electron.
No, you really wouldn't think about, well, oxygen's more electronegative than chlorine, so I'm going to make it a double bond. Oxygen being more electronegative would say, well, oxygen should definitely be on the a terminal position rather than an interior position. But really the determination here would be based on formal charges. So in this arrangement, they all have 0 formal charges, which is ideal. So there's our Lewis structure, step 1. How many groups? 3. So there's 3 electron groups on the central atom. There's a single bond, a double bond, and a lone pair, right? So how many lone pairs? 1 lone pair. We're only looking at the central atom. We don't care about the lone pairs on this chlorine or the oxygen, doesn't matter. We're looking at the central atom. So 3 electron groups. How do 3 electron groups arrange themselves? Trigonal planar, right? So there's 1 in the middle, and there's 1 up here, and 1 over there, and 1 over there. Or think about balloons, right? What would balloons do? They would make a triangle, right? So our molecular our electron geometry, we'll often abbreviate that EG. Electron geometry is trigonal planar because it's a triangle that's flat. But we're supposed to predict the molecular geometry. One of these is a lone pair, right? So let's make that a lone pair. That's a lone pair. When we look at the molecular geometry, the lone pair is invisible. Nothing else moves, but we make this invisible. And then we describe the shape of what's left. Bent. So the molecular, writing with an eraser, the molecular geometry is bent. Now that lone pair is here. We're also supposed to predict the bond angle. We predict bond angles between atoms. We're not going to predict the angle between a lone pair and an atom. So we're trying to predict this angle. Well, who's more repulsive, the lone pair or the atoms with the single bonds? Well, and actually one of these is a double bond, isn't it? The lone pair is more repulsive. So if this was perfect, the angle would be 120 degrees. But because the lone pair pushes the other things closer together, the angle here is less than 120. It's squished together a little bit. We don't expect you to predict how much. I would be hard-pressed to do that myself. I don't know. Less. It's just less than 120. Any questions? Predict the molecular geometry of I3 minus. Some of these are pretty weird molecules and ions. Well, I3 minus, there's 3 iodines. They got to be connected, so we really don't have any choice but to do that. And how many electrons do we have? Well, there's 3 iodines. They each have 7 valence electrons, and the negative means we have to add 1, right? So 22 electrons. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. What? What are we going to do? Well, let's put them on the central atom, right? So I'm going to move these guys over a little bit. Make some space. And then this is an ion, so we should put brackets around it and put a negative sign on the outside. Let's check the formal charges. So iodine has 7 valence electrons. This iodine brought in 7 electrons, and if it's leaving by cutting this bond in half, how many does it leave with? 7. And this iodine is going to be the same. How about the one in the middle? It leaves with 8, right? It's got a negative 1. Can we rearrange this so that they're all 0? This is an ion. When you have an ion, that means you either have extra electrons or you're short electrons, and so there will be formal charges. So there's got to be a formal charge. So we'll stick it in the middle. So this is okay. This is our Lewis structure. Predict the molecular geometry. Well, what's the electron geometry? How many groups are on the central atom? 5. So we have 5 electron groups. So 5 balloons. What do 5 balloons do? Trigonal pyramid, right? So, and then we've got over here, and then we've got going back and coming out this way. So this is the equator, the equatorial, the tutu. Here's her head and the feet. the axial positions. So 5 electron groups. Electron geometry is trigonal bipyramid. There are 3 lone pairs, right? Where should we put those lone pairs? Around the equator. We're going to put them around the middle because they have more space there. So this is a lone pair, this is a lone pair, and that's a lone pair. The molecular geometry, pretend that the lone pairs are invisible, and describe what's left. It's linear, right? So the molecular geometry is linear. Any questions? You have to look at the electron geometry first, because if there's lone pairs, those affect where the atoms go. If there are no lone pairs, the electron geometry and the molecular geometry are the same. So representing these things on paper, this is the figure from your book. So we end up drawing these 3-dimensional things, and that can be tricky sometimes. And so we have some conventions that we use. If there's just a single line, a straight line, that implies that the bond is in the plane of the paper or the screen. If you have a hatched or dashed wedge, that's behind the screen or behind the paper. It's a dashed line because you can't actually see it, right? It's behind the paper. And a solid wedge is coming out to get you, right? It's coming out in front. So here, the trigonal bipyramid, here's drawing a ball and stick model of it, and this would be how we represent that. So these straight lines are in the plane of the paper. This one is coming out towards you, and that one's going back behind. So that would be like, oh, there we go. So like this, where this balloon and this balloon and this balloon are in a plane, same plane as the board. This one is behind, and this one's coming out at you. Okay? So you kind of have to look at these and twist them around in your mind until you can see it. Here's a tetrahedron. We end up with tetrahedrons a lot, and so it's great if you can learn how to draw those. So we put 3 in the plane of the paper, 1 behind, 1 in front. There are harder ways and simpler ways to draw any of these. I think it's best to just choose the easiest to draw instead of a hard one. So what if you have a larger molecule that's got more than one central atom? Well, you're going to look at the geometry around each of those central or interior atoms, and that will help you to predict the geometry. So if we look at this one, this is glycine. This is an amino acid. Here's the Lewis structure. There's actually 4 interior atoms. So we can look at the nitrogen, and we say, well, the nitrogen has 4 electron groups, so it's trigonal planar, but there's a lone pair, so it's not trigonal planar, it's tetrahedral. So then it's a trigonal pyramid. This carbon has 4 bonds, 4 groups, no lone pairs, tetrahedral. This carbon has 3 groups, no lone pairs, trigonal planar. The oxygen here has 4 groups with 2 lone pairs, so that's bent. Drawing these becomes tricky, and I won't make you do that on an exam, in large part because I don't want to have to evaluate your drawings. That sounds really not fun. But you when you draw something like this, try to have as many things as possible in the plane of the paper, and then only have things sticking above and below when you have to. So let's do an example. Let's predict the geometry around each interior atom in acetic acid. Make a sketch of the molecule. So I'm going to pull this guy apart a little bit. So I'm going to take those 3 hydrogens and this hydrogen, and I'm going to draw them separately. So those hydrogens are coming off of that carbon, and this hydrogen's over here. We have to consider lone pairs, and so we actually do have to finish the Lewis structure. And just to save time, I'm just going to do that real quick. That's the finished Lewis structure. If you want to talk about it later, we can do that. Okay, so this first carbon, what is the molecular geometry? Tetrahedral. We look at that atom and it's got 4 groups, no lone pairs, tetrahedral. What about this one? 3 groups, no lone pairs, trigonal planar. And then how about this oxygen? We need the molecular geometry, bent. It's got 4 groups, so a tetrahedron, but 2 of those points are invisible, and so it's bent. Any questions about that? And then the drawing, it's fun. So how would we draw this? Well, I'm going to start with the carbon over here, and go over to the next carbon. And this carbon is trigonal planar, so that tells me that these are going to be roughly 120 degrees. So there's a double bond up there, that's the oxygen. Here's another oxygen. This oxygen has a bent structure. I don't have to draw those lone pairs. So it's going to be roughly like this to the hydrogen. And then this carbon is tetrahedral, so this has to be 3-dimensional. I've got 1 here, and I can put another one there, so I can get 2 in the plane of the paper or the screen. And then this one's going to be in front, and that one's going to be behind.